Good evening, everyone. Welcome to today's KWK talk. I request our director, Dr. B.R. Guru Prasad, to formally welcome you all.
Respected speaker of today, Dr. Klaus Mølmer, and people from ICTS, academicians, researchers, and ladies and gentlemen. It gives me immense pleasure. Let me confess that this is the first time I'm coming across such a colorful personality, I would say, because he is as much interested in literature, probably, as literature and arts, as he is in science. And the topic of today, quantum physics, the wild world of atoms. I think the wild world of atoms will not be as wild as Bangalore traffic, I think. I'm sure about it, in fact. It is better. Thank you, sir. Thanks for accepting this and gracing the occasion at Jain Planetarium. And, the thing is, I was talking to the honorable speaker today, and I was telling him the very word quantization or quantum mechanics or quantum theory. First thing is I heard about Max Planck, then Niels Bohr. I said, I still remember, it was so impressive for me. Whenever an electron's angular momentum is an integral multiple of h by 2 pi, that is what I read during my time. Now things might have refined. So that is the first time I came across quantization. Okay, quantizing something. So anyway, I don't want to take much of your time. We are extremely happy. We are extremely lucky to have you, sir, today. And on behalf of ICTS as well as JNP, I welcome you all once again. I thank ICTS for arranging it here. And this is a giant program, you know very well. This is yet another lecture under the title Kaapi with Curiosity. Thank you, sir. Please.
Thank you, sir. Yeah, before we start, I'd like to say a few words about this event. This event is trying to reach the public and convey some of the excitement of science to the public, including students, older people, and very young people also, if they have the energy and time to get through the Bangalore traffic and come here. So the Indian International Center for Theoretical Sciences has three objectives. One of them is to do research at the cutting edge of science, mostly theoretical research in physics, mathematics, biology, and computer science. And the other objective is to host meetings, like the kind of meeting which brought Klaus to our midst. And the third objective is outreach. And that's what this event is about. And we're lucky to have a person who's very much involved with outreach, Klaus Mølmer, our speaker for today. And here's a little bit about Klaus. He was kind enough to share his slides with me. He's a professor at the Niels Bohr Institute in Copenhagen. And I think Niels Bohr's name needs no introduction or repetition. He works in quantum physics, quantum computers, and precision measurements and quantum jumps. He's also written a book in Danish, unfortunately. And the book is called Quantum Mechanics, which I presume is the Danish version of quantum mechanics. The Wild World of Atoms. You might have heard about this children's book called Where the Wild Things Are. Well, that's exactly where Klaus works. And we're very happy to have him here with us. Apart from his science, which is remarkable, he's very actively interested in outreach. He likes to connect with young people, dancers, artists, and he has also some connections between quantum mechanics and music. I wish he was staying longer here, but he's here for a short time, and I look forward to this event. And he has said that he'll be happy to take clarificatory questions during the talk, but after the talk, we can have a longer session of about 15 to 20 minutes on questions. So without further ado, here is Klaus Mølmer.
Thank you very much, and thank you for the very warm welcome. It's a great pleasure. It's an honor for me to be invited. I always feel a little bit humble standing in front of an audience who didn't hear me before and who run the risk of inviting me to come here and give a talk on something as crazy as quantum mechanics. So I want to talk to you about quantum mechanics, but just before that, I'd like to say a little bit about public outreach in Denmark, because we can learn many things from India. Maybe we can teach you a little bit about outreach, because we have a super long tradition for outreach. What you see here is a map of the northern Europe. Denmark is sitting, well, I show you here on the screen with my hand, is sitting right here on the top of Europe. But Denmark is, of course, also part of a union with the Faroe Islands and with Greenland, which is up here. So we're a little bit in the news these days because Donald Trump wants Greenland. It's a big area to defend. I should actually say that there are already huge American presence in Greenland with bases and whatnot, but he wants to own it too, and that's of course a different story than owning it in having a friendship agreement about it. Anyway, outreach, since the mid-19th century, something called people's high schools were developed all over the country. There are still 75 of them in use. You see an old one here and one which is in current use. The intention was that everywhere in the countryside, away from the big cities, young people working in the farms, in industries, could go and learn something. They could pick up a language, they could go to lectures, they could learn about democracy. We had the Danish Constitution, 1849. So all these ideas should be brought out to the people. That was an ideal of priests and teachers, politicians, and it's actually alive to this very day. And it's very much the adult population like that. Some of these schools would also have kids around, but it would be mostly for the adults. And today in modern times, it's actually many people take their holiday going on a 3-week course, learn to paint, learn to do sculptures, having discussions about politics in the evening and whatnot. You can go with your family, and a lot of people do that too. And I've actually been giving quantum talks to whole families, all generations, who have spent their holiday learning about quantum mechanics and discussing politics. Just 50 years later, 1898, they developed what's called the People's University. That's around the universities where university professors and also students now present their science to people who are interested in that. So that's a 100-year-old tradition. And at Aarhus University, where I came from a few years ago, 6 days per week, you can come to the university in the evening, and there will be between 5 and 10 different topics you can choose from. Okay, so it's every week, every day, there's going to be 5 to 10 different talks. So it's actually hundreds of thousands of people who come, and it's like the movie theaters. We can see people crowding, going to the university, and some will hear about art, some about science, and some about biology, and some about food. All topics, and there will be screens telling you which room you have to go. Of course, we use the lecture theaters of the university. We're also doing massive talks, and I co-introduced 20 years ago a series of talks where we said, come and hear the hottest things from science. The first year we talked about Einstein and his physics, so of course it was 100 years old, but it was still all the modern things we do with Einstein's physics. And we had 500 people attending, which is maybe what we are today if we add the Zoom channel and you sitting in this room. But the happy thing happened that the next year they all brought their neighbors. So the next year there were 900. 1,300, 1,800, 2,300, and then we were up at 3,000 people who wanted to hear each talk, and we had to live stream like we do here today from the lecture theater. And at some point we figured we cannot house all these people in our own lecture theaters with live stream. So then we formed an alliance with all the movie theaters in Denmark. So what you see here is the 300 places where our talks are featured in movie theaters. And because we didn't want people to sit in their house alone and hear me speak, we wanted them to be together, a group like you are here, so that when you, after the talk, you can talk to each other and agree the speaker was stupid or agree that the speaker was good and have a little bit of fun together. So that's, I think, the reason people really come. They enjoy the company of each other and the ability to discuss with their friends. And the over right corner, I just intentionally kept that on my slide. I'm instructed to never put anything there because there are 4 cameramen in the room, and then they will record me and put me down there live. So that's how the talks are actually looking in the movie theaters. I zoom in on the upper left corner of Denmark, and there's a small fishing village with a special Danish tradition, actually. This is a fishing village with no harbor because they can pull the ships on the coast. Very interesting technology. There's a city with 88 people, 64 heard me speak about quantum computers. They're not going to install quantum computers in Danish fishing boats. It just shows that if you're a community, if you can have something that brings you together, it could be church, it could be handball, but in Denmark it's also science. That's really, really a nice thing. So I love that. And now I want to talk to you about quantum physics. So first I'd say a little bit about classical physics, what came before. Then I talk about Planck. We already heard Planck's name mentioned. He is the one who coins the name quantum because he makes the theory for light, which introduces quantumness. And I'll tell you what it is, of course. I talk about Niels Bohr's model of the atom, and then the real quantum mechanics that came in the 1920s. The famous discussions between Bohr and Einstein, I'll say it right away. Bohr and Einstein never agreed on the interpretation of quantum physics. Quantum physics is strange. It comes with many different interpretations, as life does. And people disagree because we can have different personal experiences that also make us prefer one or another interpretation. And Bohr and Einstein had completely different views of what they wanted the theory to look like. They completely agreed about all equations. They completely agreed about everything we do with quantum physics. They just didn't agree with what it means. And normally I joke, they discussed it until their entire lives. Einstein died in 1955. But of course, Bohr is still discussing with Einstein after 55. So he's still writing answers to Einstein's questions until Niels Bohr dies himself in 1962. So I'll talk a little bit about that. And then I'll go to the physics of the 20th century. What did quantum mechanics really do for us? And it did one thing, and that's always very important when you talk about quantum. It's not only the strangeness, it's not only the philosophical discussions, it's actually the quantitative theory. It's the reason that my friends, the astronomers, know the temperature and the processes in the stars. It's the reason that we know today how biomolecules function. All these things are microscopic phenomena at the level of nuclei or atoms. And it's the understanding of these phenomena that quantum mechanics is really about as a real quantitative theory. So that was the physics of the 20th century. And there was also a technological revolution coming with the understanding of the microscopic world. The transistor, the laser, all these things are quantum machines, right? And now we talk in the 21st century about the second quantum revolution. And that's a revolution where we are going back to the Bohr and Einstein discussions and the craziness, the oddities of quantum theory, and ask, is that also a resource for something? And it is a resource for what we call quantum computing, quantum cryptography, and some other schemes. So I hope I can make it through this program with you and tell you a little bit about all these epochs of the development of quantum physics. So before quantum physics was classical physics. And classical physics is not terribly old, actually. The real understanding of mechanical motion comes back only to Newton, 1687, where he wrote his famous big work explaining how mechanical motion is actually governed by physical law. And the most important equation, I think, in all of sciences is Newton's second law. It says that the force on an object is equal to the product of its mass and its acceleration. Now, acceleration means, does it move faster or slower? So if you know the velocity of the particle, you know if it moves faster, also how much faster. So you can actually calculate the trajectory of a particle if you know the forces on it. I can calculate when a stone will hit the floor if I drop it. Right? And I can calculate many, many things. And Newton could calculate planetary orbits. And he could calculate mechanical phenomena on Earth. It's very famous that he also had to invent one of the most important forces, namely gravity. And that's the force who explains why apples fall to the ground. They don't fall to the ground because they like to fall to the ground. They fall to the ground because of that equation and because there's a force that pulls them, which is the force of gravity. And it's the same force. Well, actually, this is the tree that's still alive, the tree from the garden of Newton. But it's also the same force that keeps the moon in orbit around the Earth. And I made just a little illustration of that. So if you're standing on a high mountain and you drop a stone, then of course it will fall to the ground. And that's the normal gravity like the apple. If you drop a little bit harder, then it will fall a little bit longer. Right? And I do it a little bit longer again. But what if I do it even stronger? Oh, it can keep falling down and down and down, but it just follows the curvature of the round Earth. And now it is in orbit. So all these orbits, also the moon's orbit around Earth, the Earth orbit around Sound, is actually freely falling object. It just has enough velocity to make it around instead of falling down on the Earth or the planet or the Sun. And that was all back to Newton. So impressive physics, and we are all standing on the shoulders of Newton. There's another branch of physics which is also important, and that's the theory of actually electric phenomena. electricity and magnetism. Physics going back to the 19th century. And I just show you here the theory of light. If you have light, you all know the rainbow. You also know if you put a piece of glass in a window, you see a little rainbow sometimes after the glass. That's because water in raindrops or glass bends the different colors of light. So white light coming in from the sun is actually composed of many different colors, and they take different trajectories and different directions through glass and water. So that means that the white light, the different colors will come out in different directions. So if you imagine in the sky that the sun hits the raindrops, then the different colors from the sunlight coming from behind you will go out in different directions. That means you have to look different places to see the different colors, to see exactly these deflections here. So that's beautiful. The theory for light, the true theory of light, was established by Maxwell back in around 1850. And he says light is an electromagnetic wave. It's electric field, magnetic fields. The colors correspond to the frequency or wavelength of the light. So a wave is a wavy phenomenon that goes up and down. The electric field is getting stronger, weaker, stronger, weaker, stronger, weaker. And the period is what we call the wavelength, from peak to peak to peak. And if you have a short distance, it's more like the blue light. If you have a longer distance, it's like red light. If it's even longer, it's microwaves in your microwave oven, or radio waves that we hear from the radio signal. If it's even shorter, it's X-rays. So all these phenomena are actually the same, but they operate on different color scales. So here's the spectrum of light, and this corresponds then to the longer wavelengths, and this is to the shorter. This corresponds to the higher frequencies, this to the lower frequencies. That was very well known and understood at the end of the 19th century, but there was a few things that were not so well understood. And it's actually quite remarkable because it's a phenomenon that we must have known for a million years. Here is a fireplace. And you know when you have fire and it gets colder and colder and colder, it turns more and more red. Okay. Now physicists, we are really nerdy fellows. We want to understand everything around us. So we would also, of course, also like to know why is a lower temperature fireplace red and a hot one white? And there was no theory that explained that. Okay? There was, of course, an understanding that it would be the shorter wavelengths or the higher frequencies down here, but that has nothing to do with the intensity of the light, which is more about how strong it is, but not what the frequency is. Okay? So that was a mystery, and it was literally a mystery at the end of the 19th century. And then came, so I call it the mystery of the fireplace. Why is cold glowing red while hot is glowing white? The answer came by Max Planck, year 1900, and he was a younger man at that time. I apologize for showing him as an old man, because he later was fortunate enough to become an old man. But as a younger scientist, he discovered that there's a connection between the light and energy and frequency, which goes beyond intensity. He invented actually what he called the quantum of light, being like single particles of light, and the energy of a single particle is proportional to its frequency. So that means that these particles, if you have particles here, they will have higher energy, higher frequency, lower energy, lower frequencies. And at low temperature, there's less energy present. So therefore, you have the lower energy, and therefore you are dominated by these light particles with the lower energy, which are the red ones. While if you go to the higher energy, there will be more energy available, and therefore you will be dominated by the other colors of the spectrum, because they correspond to high energy. Nobody had seen these quanta. There was no obvious meaning. What does it mean to have this? But he called it a quantum. And you know, the word quantum is used in daily life, and now it's used everywhere with reference to quantum. But if I go to the supermarket, I can buy a cucumber, but they will have a quantum discount if I buy 3. So that's the amount you buy, but it's always discretized. I cannot buy half a cucumber. I can buy 1 cucumber or 2 or 3. And the same with this energy in light. There can be 1 of those, 2 of those, 3 of those quantum in light. And Planck was not only realizing this connection, but he also realized that it was so important that he put the word quantum in the title of the article he wrote. There was a quantum theory of light, even though it was not clear what these quantum precisely were doing. But now I want you to think about light as being composed of a form of energy particles who have a very definite energy. And that was discovered 1900. So light is a wave still, but it appears in these little quanta. And when you see light, for example, from the sun, then you see a big, broad spectrum of colors. This is how much intensity at different frequencies or different colors. The orange curve is a formula given by Planck. The red curve is the actual solar spectrum. And there are reasons for these deviations which are clear, but some of the deviations I want to talk a little bit about is these dips. So they are clearly a deviation from the orange curve. But that's because there are some matter in the atmosphere that absorbs these particular colors of light. So the sun spectrum is actually pretty broad, and then when it travels towards us, it loses some intensity because it gets absorbed on the way. A bit like if you have colored sunglasses, the world looks red or it looks green because you filter away some colors. The atmosphere filters away some very specific colors corresponding to these lines. And two great scientists who helped discover that were actually Fraunhofer in Germany and Wollaston in England. So they built devices so they could show these spectra very precisely. And we are talking early 1800s, 1804, 1810, where these experiments were done. And now, since then, we have actually been doing this spectroscopy, as we call it, where we take every light source we see, we pull at what is the color content. And this is this full solar spectrum, just cut it up from all the rainbow colors. But you see many stripes. And there's actually 100,000 known stripes in this spectrum corresponding to light going mist. Okay. And also in the mid-19th century, we actually knew what was these lines. This orange line here was immediately identified as absorption because there must be sodium atoms. And how could we know? Because if you go on the planet Earth and you heat up some sodium, you see the same orange light. If you throw salt into a candle, you will see flashes of orange. That's actually
detective work that lets us know that sun and earth originated from the same material, because we have the same fraction between gold and silver and silicon and all the elements in the sun as we have in the earth. Okay. There was one element that we never saw on earth. There was a new line in the spectrum. Actually, there were a few new lines in the sun spectrum. One of them had no correspondence on earth, and they named this element after the sun. Now, sun is helios in Greek, so therefore they called that element helium. And 10 years later, they discovered helium for the first time on Earth. So isn't it fun that there's an element, an atom, that's discovered 150 million kilometers away before we find it in front of our noses? You'll know why, because if you put helium in a balloon, it can lift the balloon away. So helium is not in the atmosphere, it flies out of the atmosphere. And I end up here with this picture of the James Webb telescope, which is one of these famous telescopes in space. And it's looking into space and it makes beautiful pictures. But actually, every single dot in that picture is spectrally resolved. So they know what are all the atoms on all the stars we see in the universe. So it's part of a very big story, this fingerprinting of how all objects.
a prism, then you will see only very specific colors and the same places where there will be absorption if you send light through the same gas. And this is Niels Bohr as a young man who in 1913, he was 27 years old, made the theory of the atoms. Okay. And the theory of the atoms is building on the discovery of a tiny light negatively charged particle called the electron 13 years earlier by Thomson at Oxford. And 2 years earlier, Ernest Rutherford had discovered that matter, even though you think it feels smooth, it's not smooth. At a very fine scale, it's very grainy. There are small, very compact objects called the atomic nuclei, and Rutherford had found these nuclei. They're positively charged, heavy, compact particles. So Bohr, he had just two ingredients: light, negative particles, heavy, positively charged particles. They will attract, and he suggested that it's like gravity. They will form planetary systems. So this is the Bohr model of the atom, which maybe you all learned about in school because it's how we describe atoms. So, but it's very, very new in 1913. So he says the electron is of course orbiting this sun or this planet here because of the force between them, which is electric in nature. But that does not explain why the atom has only certain frequencies. If you think about things flying around Earth, they can fly at any distance. You can fly just above the surface, like the space station. Then you have a period of 1.5 hours. But you can also go out at 40,000 kilometers. Then it takes a day. That's why they're stationary in the sky, those satellites. Or you can go to the moon, and then it takes a month. And that's why we call it a month and moon. It's the same word, because they're sitting, the month, moon is that distance. So different orbits here would have different frequencies, but of course they could have any frequency if you just move them closer or further away. So Bohr was a brave young man, because he said we have these orbits as in planetary physics, but there are only definite ones of them. So that's a postulate. It's not physics. It's just saying must be like that. And then they are stable, and by stable he means that you can fly around here forever without losing energy. So there's absolutely no signal coming from you moving around in that orbit, because that would be energy. But there's another thing happening, says 27-year-old physicist. He says, maybe you are in this orbit, but you can jump to the next one. Crazy. There's no physical laws that say you can jump from one orbit to another orbit. Imagine you could jump through Bangalore traffic the same way from one road to another road. It doesn't work like that, but this is the postulate of Niels Bohr. And when you jump, for example, for the n equal to 2 orbit into the inner one, this one has lower energy than the other one, or the one further away. That energy is conserved because you emit the energy as light. Okay? So there's always the same energy present. Either a lot of energy in the atom, it gives away the energy to light who goes out, or you can also absorb light when you're in that state, and then you jump to the higher energy state. But for that to happen, you must absorb a photon with the right frequency, because you need the energy of that photon to go out to that orbit. And this is why that atom can only emit certain frequencies. It can only absorb certain frequencies, because you cannot absorb any other number, because energy will not be conserved. So that's Bohr's model of the atom, 1913, and the energy of these jumps is exactly Planck's formula. It says that the frequency of the light has to match such that Planck's constant times the frequency of light is the energy difference between these orbits. So now you can actually find out where they are in an experiment. And Bohr also made a theory to calculate where they are. And that's the legacy of his work, 1913. In fact, it gave much more than that, because it also explained how the different atoms react with each other. So this is Bohr's model of the atom with the electron moving around. If you have 2 electrons, 3 electrons, 4 electrons, the bigger atoms, then 2 electrons cannot be in the same orbit. They have to be all in different orbits. And Bohr could calculate all these orbits. And then he could find that for some atoms, they would together, the neon atom here, fill up 10 orbits, and those 10 orbits would all form an almost perfect spherical shell. So that means that the neon atom will be very close around itself. It's actually what we call a noble gas, and it acts very little chemically with other atoms. Of course, we already knew that neon was a very inactive gas, and in Mendeleev, who invented the periodic table, he had categorized atoms according to how reactive they are. But now came Niels Bohr and gave an explanation. This one is inactive because it has this closed shell of all these electrons. If I add just one more electron, I get to the sodium atom. Mendeleev did not know that that was due to electron physics, but actually in the sodium atom and in Bohr's model, the next available orbit is this big one. So that means the sodium atom is carrying 11 electrons, but it's not just 10% more than neon. It's actually neon plus a very wild electron who's making huge orbits. And that means that sodium is going to be much more chemically active because it stretches out to other atoms. It makes molecules and makes salt and all these important things. It's actually dangerous sometimes to have nature sodium around. So wow, very, very good, very nice. And it's such a wonderful theory, and it's really a breakthrough to understand atoms and molecules. For hydrogen atom, Bohr's theory fitted with this precision, ridiculously high precision. The best precision ever at that time predicted for anything and measured in the lab, the frequency of light from the hydrogen atom. But then when Bohr tried to do the same for other atoms, like helium, who has 2 electrons, he was off by 10–15%. And nobody could get it better than that. And he was literally having many, many students working with him, and he was wearing down those poor students because their project was to work on doing this better. And they never got it better for almost 10 years. And they actually had to abandon the Bohr theory for the atom. So sorry for taking your time. On the Bohr model, it's wrong. Okay, but it's wrong for a very exciting and very good reason. Bohr had been lucky with the case of hydrogen, and it didn't work for other atoms. We have to do some completely new. I mean, we have to solve helium, right? Otherwise, our theory is not a good theory. And you have to think completely differently. And the gentleman who did that was Louis de Broglie, French scientist, who took a different view on the Bohr orbits. I'll show it on the next slide. And that was then passed on to Schrödinger, who used the de Broglie idea very literally, and another version by Werner Heisenberg, something called matrix mechanics. De Broglie introduced a wave understanding of Bohr's theory, and Schrödinger made a theory for those waves, which I show you now. So de Broglie, he looked at the Bohr orbits, and he said, there is actually a simple rule, and Bohr also noted that rule. Any of these allowed orbits have the funny property that if you multiply the mass of the electron, the velocity of the electron, and the circumference, how long is it around that circle, then you always get an integer number times Planck's constant. You get 1 times Planck's constant, 2 times Planck's constant, 3 times Planck's constant. And all these orbits that I showed you before for neon and sodium are orbits who are beta. So that was just a fact of the Bohr model, and we sometimes call it the Bohr quantization rule or Bohr-Sommerfeld quantization rule. But de Broglie, he said, why? Why does it have to be like that? And then he said, well, it could be if it was not really just a particle moving around, but maybe a wave that is biting its own tail. So you can see here, I've tried to draw Bohr's orbits again. And if you imagine that you can just fit 1 wave or 2 waves or 3 waves or 4 waves, such that they periodically rewind and bind to their own tails, then that could be an explanation, at least a beautiful aesthetic explanation of what is special about these orbits. If I took orbits in between, it wouldn't fit, right? But for those, it's the ones where it actually fits. So de Broglie was touring in Europe with this idea, and it spread, and people were talking about it. And then, of course, we have to make now a theory, which is a wave theory. So which physics, which law, which equations govern those waves? And that became the birth of quantum mechanics. And it happened in a very funny way now, because we are not making physics for a thing we know. Actually, we don't know what we want. Now we think something is waves, so let's make an equation for waves. Okay. We don't know what is the wave. We don't know what the wave is doing and why it is a wave, but let's just do mathematics for waves and then see what comes out of that. So if you have waves like water waves, we actually have a theory for such waves, because it's something with Newton's laws acting on every little molecule of water. If you take the strings on a violin, there's also wave motion. And again, it's Newton's laws, because it's forces that are pulling the string. So these equations, but they're harder, because of course the string is not just one particle that feels a force. Every particle of the string feels different forces. So that's why the string can have all different shapes when you play the violin. And the same with the sea surface. So it's going to be complicated, but we have theories for such waves. And just looking up what these equations look like, Schrödinger tried and tried, and then he ended up with this equation. And that's the Schrödinger equation. And for those of you who don't know the Schrödinger equation or don't know mathematical equations a lot, don't worry. There's not going to be any exam afterwards. I just want to say that this equation is fantastic. It is the force equal mass times acceleration of quantum physics. It is the governing equation. And it's very abstract because it's a theory, an equation for a wave. So the object we are looking for is this cactus. It's a Greek letter called psi, and it's a function of space and time. And that's because if you have a wave, the height of the wave is a function of where you are with respect to the surface. But it's also a function of time because it changes all the time. So we are now looking for that description of that wave. And that is going to be a function of space and time. And it solves an equation, and I'm interested in knowing how does it change with time. If I know it now, what will it look like next, and next, and next? Because then I can predict your experiment. And the left-hand side actually asks, what is the rate of change? This is what this symbol means. So this is the change per time, sorry, that's a Danish word, per time of the function here. So that's what you need to do. And then inside the equation is this crazy object, which means how does it vary with space? And I just explained to you with water. If you have a flat surface, and you look a little bit later, it will still be a flat surface. But if you have something like that, you know that that water is going to spread out to the side, right? So the more curvature, the more the surface is going up and down, the more there will be motion trying to equilibrate that. That is what is measured by this term in the equation. The last term, this V, is actually where the forces acting on the particles enter. This is called the potential energy, but it's a function of the forces. So Schrödinger tried different equations. He arrived at that one, more or less his second try, and then he solved it to see what he got. And so here's the equation again, and here are some of the solutions of waves which are just standing, going up and down, like the vibrating string. And these are the solutions. The more interesting thing about these solutions is, of course, well, first of all, they look very nice, and I just point out two of them here. There's one here with some bigger structure that goes up and down, and there's some more complicated structure here. Here's a picture of a guitar playing two tones, recorded with a police radar. who sees how far its surface is moving. And if you look at the guitar, you can see it has exactly the same pattern. It has, for the deep tones, this pattern going in and out. And for a higher tone played by a guitar, the surface of the guitar, which is like the loudspeaker of the guitar, is actually vibrating in the same pattern as this quantum down. Because the surface of a guitar is doing wave-like motion. It's a surface which is vibrating like a water surface is doing. So you can see there's not even anything new in quantum mechanics. All the solutions we find look like solutions in classical wave phenomena. So, and if you solve it for the case of hydrogen, putting the right forces here, you get out of Schrödinger's equation exactly the same frequencies as Bohr and experiments. Hooray. If you do it for helium, you also get the same as the experiments. You don't get the error that we had in Bohr's model. So this is the right theory. And this is the equation we solve in all of microscopic physics until today. And it's not because we are conservative and hope that we will not find errors. We hope we find errors. That's the next famous physicist, of course, who finds the error, because then that physicist has made a really important discovery. So we are very sorry to say that this equation is so as good as it is. But of course, we're also happy that we have a good theory. So what is the wave function actually about? Okay, now I just showed you the frequencies were right, but what does this wave mean? And it has nothing to do with John Travolta. It has a little bit to do with Olivia Newton-John, because her grandfather was a German physicist, and his name was Max Born, and he invented the interpretation of the wave function back in the 1920s. He noted that the wave function itself, the mathematical function, the absolute value, the square of that number, is actually giving you information related to what you see in experiment. So if I do an experiment where I shoot many, many electrons through a little hole, and I saw the Schrödinger equation, I find a beautiful wave-like pattern, like the ones we saw before. But this is not a theory curve. This is actually millions of little white dots, because in the experiment, there will be first a white dot here, then here, then here, then here. And if you accumulate really many, you can see they form a pattern. And that pattern is the wave function. So in every single experiment you do, there's a probability to end somewhere. And if you do a million experiments, that becomes a distribution. But in every single experiment, you cannot predict what is the outcome, because it could be anywhere on that screen. More likely in the big wider blobs, but it could be anywhere. But in the dark zones between the rings, you never see the electron. So it's a very strange theory. It's a theory who doesn't tell you what you will see in the experiment, but what you may see in the experiment and how likely you will see one thing or the other. And that's what the wave function means. And this is where it gets complicated. I mean, it gets complicated for physicists because we don't like physics to be about randomness. But life is very much like randomness. You can think doing quantum physics is a bit like tossing coins, where we also don't know what to get. But if it's a fair coin, we get heads and tails half of the time. So we can make casinos, and we can make games, and we can also make insurance companies who can do probability theory. This is electrons in the 30s. This is a real picture. This is a real picture where it's entire molecules who, even though they're very big, can also sort of, so to speak, be described by the wave function and end up in very nice patterns that looks like waves. So it's a precise theory for random results. This is why I actually didn't draw it, but I designed this figure myself. This is Bohr's model of the atom. This is Schrödinger's model of the atom. These dice here is to indicate that you get random outcomes, and I'll come back to the cat maybe a little bit later. The Schrödinger equation gives energies with enormous precision. We can completely tell you what frequency of light we see. Today we have calculations with 12-digit precisions that we can actually compare with experiments. It's quite amazing. But we cannot tell you where you see the particle. Then you have to go back to this probability assumption. So that's the order of life, how it works here. And Einstein was particularly unhappy, and he asked Bohr at some point, do you really believe that God plays dice? Is it really random? Is it truly random? Or is it actually already given? We just don't know what the outcome is going to be. And that's the Bohr and Einstein discussion. So I just show you here, let's say that this red curve is the probability prediction. This is the wave function I show you here. And if you do many experiments and you record where was the particle recorded, they will form this distribution of data points. And that's what we confirm in the lab. Einstein, he said, you have only one particle. So maybe could it be because the particle is just flying around, and it just happens to be so that when you measure it, it will be for natural reasons more likely in some places than others. My little cartoon had spent most of its time where this wave function was big. And that could be true, right? Schrödinger, who invented the wave equation, in the beginning he actually thought that the electron had become a wave. right? So it's just because you are a wave, but then that cannot explain why you see it localized as a particle. So then we have to explain why it looks classic. Schrödinger then had to sort of develop first an idea that maybe the wave function contracts. And that is what we also call the collapse of the wave function. But it's also, okay, it's opposed and very different interpretations of quantum mechanics. And Bohr, I'll tell about him on the next page, but since this is the place I never have anything important on my slides, I just showed that we also had him on our money at some point. And we were politically incorrect enough to let him keep smoking, because he was always smoking. In 1927, there was a clash between the physicists. This is Schrödinger and Heisenberg being at the conference. This is Ehrenfest, also a famous physicist of the time, and it is fun to read his letters about the conference. So he gave a report to his colleagues back in the Netherlands, and he writes about Einstein, who's sitting there, that Einstein came fresh each morning like a jack in a box with new arguments, fighting quantum mechanics. And Bohr, who we also see in the picture here, he always smoking on his pipe, coming out of philosophical smoke clouds, crushing one argument by Einstein after the other. It was priceless, according to. And in fact, if you look at Marie Curie and some of the more senior scientists, they look pretty grumpy. So I'm sure they did not enjoy the discussion as much as the younger physicists did. But anyway, this is 1927. And Einstein at that conference brought up what we call thought experiments. So it's not a real experiment. It's just taking the consequences of theory and see what they would lead to. Right? If this is true, then this would be true, then this would be true. And how can you explain that, dear Niels, when he talked to Niels Bohr? So Einstein is imagining a wave of particles, or Schrödinger equation, who has a whole wave pattern here, and then it hits a screen with two openings. So that means that the wave can leak through this hole and that hole. And when you look down further down, there could be what we call interference between what comes from the lower and the upper path. And that actually, by prediction of quantum mechanics, leads to a prediction of stripe patterns, a bit like the fringes I showed you before. And Einstein's question was, of course, if I find a particle who hits the screen here, did it go through both holes? Did it go through one of the holes? Or is there any way to tell if it did go through one of the holes? And he made all kinds of funny versions of this experiment. You can see there's a little door here you can close and open, just to discuss what happens if you can do that. And he did many other things. I'll not go through those in details, but the very question, if it was in any way possible to know which way it goes and still see it hit the screen within this pattern, then there would be information that the wave function does not tell us. Because the wave function is in both holes. It has the same value in both holes. So it does not say, but in real life it actually went the other way. So Einstein is asking for this extra information. It's sometimes called a hidden variable in discussions of quantum mechanics. And generally, this which way did you go versus do you see interference fringes or not, that's the which way particle type view versus an interference, which is a wave phenomenon. So there's a clash between the particle and the wave picture. And it's not correct to say that quantum mechanics turned particles into waves. They are still particles because we detect them as particles. So it's a duality between two conflicting ways of describing the world. And Bohr introduced the concept of complementarity, saying, in fact, I mean, there are different phenomena where one picture is the good one, the other one is the good one, but they have to be used both to completely exhaust what we know and understand about the physical system. Einstein had a second thought experiment. I just have to show it to you. It's a little bit complicated, 1935, but it's also a fantastic experiment. Einstein said, let's just imagine two particles described by quantum mechanics. We imagine they fly apart, but of course they're quantum mechanical, so they're not like localized. One has a big wave sitting over here. I don't really know where it is within this wave, and the other one has a big wave over here, and I don't know where it is within that wave. But physical laws could say that they have to be at the same distance to where they started. So in fact, there's a wave on both sides, and they're correlated. Now, I measure this one. And I measure it randomly to be at a particular location. Instantly, I also know that the other one is at the same distance on the other side. And now Einstein discussed the physical process. What is it that happens when this wave contracts and becomes point-like? And what Einstein finds very, I would say, disgusting about this situation is he never touches that particle. He touches a particle over here when something happens to a particle over there. And he thinks that is really odd. There is another solution, he says. The other solution is both particles were already in well-defined positions. We just didn't know where. And when I measure this one, I just happen to learn both where that one is and where the other one is. In the classical world, if you have two like objects, right, but you don't know if, well, I use my feet always. I say, I have socks, but I never remember which color are my socks. But of course, if I look at my left foot, typically, I also know the color of the sock on my left foot. Right? So that's because they just have random colors, but they're the same most of the time. So this is the Einstein clash with quantum physics, and he actually suggests that maybe the positions we measure are already well defined. They are real elements of the theory, except that they're not in the theory, because quantum mechanics doesn't tell what is that. And he called that an element of reality. If you could define a quantity in this particular way. Alternatively, Einstein says there is a remote action. So when you actually do this measurement, something literally happens on the other side. He called that spooky action at a distance because it would be so weird. It could be inside a metal cage. There could be no way to signal or communicate any forces into that box. And it could be a light year away. And we actually see these effects now with light year distances in astronomical phenomena. So these correlations actually do exist. And that's scary to Einstein. So he really pushed Bohr. The wave function description does not give a complete description of the physical system, because if this correlation is true, there must be the true values, more or less pre-assigned, before we do the measurement. And Bohr, he says, of course, there's no question of a mechanical disturbance. So there's no spooky action at a distance. In Bohr's mind, he says, and now it gets difficult because Bohr's language is always fun. There is essentially the question of an influence on the very conditions which define the possible types of predictions. Now I cut off 1/3 of the long sentence and it continues the same sentence. These conditions constitute an inherent element of the description of any phenomenon to which the term physical reality can be properly attached. Now what Bohr is actually saying here is that what happens when I measure that particle is not a physical effect on the other particle, but there's a thing that happens to the conditions that make me predict experiments on the other particle. Something happens to my knowledge when I measure this particle. I know where it is. When I know where this one is, I also know where the other one is. Nothing happened to the particle, but something happened to my mind. I learned where it is. And quantum theory is a theory about what I know and what I can predict in experiments. And Bohr calls these conditions, and they define predictions. So when I measure this particle, I know where is the other one. I can predict, measure it, and you measure it in that location I'm telling you. But for Bohr, there's not a thing happening in the physical world. It's very, very abstract. But he says physical reality is actually what we measure, and not necessarily our metaphysical description of what small particles are doing. Maybe we will never find that picture, and Bohr will live with that. And I'll just put that on the next slide too. It's briefly what we call the Copenhagen interpretation. This is the Niels Bohr Institute in Copenhagen. That the wave function here represents only our knowledge about the system. There's not a physical equivalent object. There's not a wave in the microscopic world. This is just at the level of representing my knowledge. Here is a cup and there's a dice underneath. It has 6 possible faces, and we can make guesses about which one is facing up. If I ask you what's the probability that it will be 5, you will probably all say it's 1/6, right? Because there are 6 different possibilities. The same as for what's the probability that it's 3 or 4. And now I lift the cup. And now it turned out to be 5. So now the probability is 1. So we started out having a probability which was low for all 6 possibilities, and now it all collapsed and became 100% on only 1. That collapse of that probability distribution, was that a collapse of the dice, or was it a collapse of our knowledge when we saw the result? I would call it knowledge, right? And that's the same way that the Copenhagen interpretation says that measurements are done in quantum physics. The mystery of quantum physics is that the dice actually had that phase pointing up all the time. While in quantum physics, we cannot even talk about it because we don't have a physical description of the physical particle anymore, because the wave function is not the particle. The wave function is my mind. And what Einstein tried to build his whole life was a theory for what the microscopic world is actually doing. And many of my colleagues are still making candidate theories that can go hand in hand with quantum physics. I usually say if all the quantum mechanics textbooks were only written on the even pages, then on the odd pages, we could write what is really happening, right? But many people have tried to write those odd pages. And there are suggested, we have 20 different interpretations of quantum physics, and some of them fill out those odd pages. They disagree in Copenhagen. They more or less define themselves as being in opposition to Copenhagen, but they actually disagree much more with each other. Because, of course, they actually say this is what is happening, and the other guys say this is what is happening. And Niels Bohr doesn't say that these are not happening. He says, I don't care what is happening. I only care about experiments, and for that, I only need a theory that tells me what comes out of experiments. So there's actually not even a conflict between Bohr. The conflict is, that Einstein can never understand why Bohr doesn't want to understand what happens physically. And Bohr's famous reply to that is, I don't need it, because the theory already gives me every agreement with experiment. Heisenberg, who was, of course, inventor of physics, he was on Bohr's side. Because he's German and has read philosophy in Germany, he can formulate it very elegantly. The abrupt collapse of the wave function is a consequence of a transition from the possible to the real. I think that's a beautiful sentence, but of course it doesn't enlighten us much. Here are some quotes about quantum physics, and they're not jokes. Einstein said, if quantum theory is correct, it signifies the end of physics as a science. This is Schrödinger. He invented the theory, right? I do not like it, and I'm sorry I ever had anything to do with it. And Schrödinger actually went and did other things in his life. He essentially invented the DNA, right? So he went out of quantum physics. And Bohr, those who are not shocked when they first come across quantum mechanics cannot possibly have understood. It is a strange theory. But it's also a good theory. We can do all this quantitative description of atoms, of nuclei who have particles inside of them, protons, neutrons have quarks inside of them. All of this is quantum theory. All of this is the Schrödinger equation in one form or another. We can put atoms together, and then they will form molecules. And we can put atoms and molecules together, they will form solids. And our physical theory of all these objects is the Schrödinger equation. Yeah. Yeah.
You say that you've seen this collapse in astronomical phenomena.
Yeah.
Doesn't that cast questions on Bohr's interpretation?
Well,
Because you're saying that Bohr's saying that you just know that if you did a collapse here, that would be there.
right. Yeah,
All right.
but I just asked because it was myself carelessly just saying we see something of this in macroscopic phenomena. So it's exactly true what you say. So and we have to be very careful. We always only see what our measurement apparatus tells us. But of course, I can have measurement apparatus who looks into the sky in different directions. And due to the gravitational lensing, which is a funny effect, the same source can actually send photons along two different paths. So in the sky, you sometimes see two stars, which is only one, because it goes around a black hole or a galaxy. Sometimes you see a whole ring, which is the same star because it takes always around that black hole. And if you look at the correlations between these photon measurements, you see the same kind of quantum correlations as we see in lab experiments where we very controlled look at two different points. So the reason for the correlation in Einstein's experiment was that they had a common past. They were moving away from each other and they kept that history. While in space, we typically do first one measurement and then we establish a correlation and then the second measurement shows, oh gosh, now they are correlated. But let's discuss it briefly afterwards. Well, it's very quantum optical effect, as we also call it. So this is quite fantastic. Now, I apologize that I just skipped this little Dirac side. It's not your fault, it's my fault, because I always love to tell the story. I get so excited. I spend a little too much time, but I have only 10, 12 minutes left, and therefore ask me about Dirac, but it's such a wonderful story. So by all means, ask me about the Dirac equation. But I just want to scroll through it and then talk about a little bit about technologies. So all of these things also are technologies. There's a chemical industry, there's nanotechnology, there's computer chips, there's radiation therapy with radioactive nuclei, there's nuclear power, there's diagnostics, all the way down to the fundamental elementary particles. So of course, these are things we understand and use because we have a theory and we know why it works. This is the modern arena for quantum physics. You want to optimize solar cells, which is a microscopic process where sunlight energy should be transformed to electric energy. You can see it's every ingredient of quantum physics. It's exciting electrons with light energy, quanta of light, making it work for all colors. After that, what are we going to do with that energy? Well, we are going to take, for example, CO2 out of the atmosphere, together with water and nitrogen out of the atmosphere, and form useful components. Not only take it away, but actually build fertilizers, materials, pharmaceuticals, which also use the elements carbon, for example, and other nitrogen. And so that's the agenda of very important physics, which is quantum physics. And now the 21st century, the second quantum revolution. And this is a hot topic. You get the elevator pitch here, right? So I'll tell you about a few fancy experiments. And you saw these big talks we give in Denmark. I give a 2-hour talk with the same big audience, which is only about quantum computers. But you get the fun part of the quantum. They get the boring part of the quantum computers. The reason we talk about quantum computers is that in the mid-90s, this gentleman, Peter Shaw, and this gentleman, Love Grover, came up with 2 algorithms that could benefit from a computer that runs with quantum systems. And what is that? That's a computer in which you use wave functions to describe the data. And a wave function means that you can be in two positions at the same time. You can be a 0 and 1 as much as you like if you're a bit. And if your data bit can be 0 and 1 in the right way, then in fact you're calculating two numbers at the same time. And if you have many bits, you calculate many numbers at the same time. And it's not as easy as I just put it, because you also have to read out the machine in the end, and then you get random numbers. But those gentlemen found two algorithms where the probability to get good numbers became high. Okay, and we don't have many algorithms. We have one more algorithm on top of those two, which is seriously being discussed. So quantum computer can do something, and they can actually here do some interesting math, sort databases, and they can find factors of big numbers, but they can also be used as simulator for a lot of quantum physics. So we can do chemistry with them, solid state physics, particle physics with a quantum computer, mostly because that what makes these problems difficult is that they are quantum. So they actually have the same property as your computer. So you're actually matching the ability for your particles in your computer to do the same as the particle in the physical system. And then the classical problems that today also relate to machine learning. So the quantum computer, in very brief, is replacing the classical bit. I draw here a little abacus just to have a nice drawing of it. If it's on the left, it means 0. And if I put it to the right, it's the value 1. But on the quantum computer, we have a wave function for it, which could correspond to having 0 and 1 at the same time. We call it superposition. And then you can perform a computing with several numbers. And let me do a very boring math to you. If I have one quantum bit, then I can have 0 and 1 at the same time, two values at once. If I have two of them, I can have four values at once, 0, 0, 0, 1, 1, 0, and 1, 1. If I have 10 quantum bits, it gives 2 times 2 times 2, 10 times. That gives 1024 calculations that you can do at the same time. And if I do 100, and that's the last one I give you, then that would be a 30-digit number of computations you could do at once with only 100 bits. Right? Here is the world's largest supercomputer in Tennessee, America. It's called Frontier. And it consists essentially of normal chips like my laptop. They do 3 billion operations per second. That's why it says 3 gigahertz on your computer. But that's also your computers. Some of the phones are also close to these frequencies. But then they have 10 million of them. And when you have that, then suddenly you can, of course, in parallel do really many calculations. So it actually does 150 billion calculations per second. 150 petaflops. That's a 17-digit number of calculations per second being done by that machine. Impressive. But let me just remind you on the previous slide, 100 bits. If they did only one calculation per second, they would do a 30-digit number of calculations per second. It's 10,000 billion times faster than the world's largest supercomputer. And it runs one calculation per second on 100 bits. It's crazy. But that's because it does it all in parallel on that single unit. So this is the promises. That's the elevator pitch about quantum computing. Now the true story is, of course, we have to find the algorithm. And another true story is we have to build it. So the quantum computer has to be built of quantum particles. Otherwise, we cannot do the calculations on it. So there are ideas, and this is one of the first quantum computers to use molecules. I just show you the molecule here. Every of these little colored atoms here, they are the bits in the computer. They have a degree of freedom, the nuclear spin. And these nuclear spins is actually up 0, down 1. And they can both be up and down at the same time in a crazy quantum way, and they can do calculations. So this gentleman, Ike Chuang, he actually factored 15 into 5 times 3 using this substance of molecules 20 years ago. Of course, we want to do bigger calculations at what are the factors 15. So we maybe want to build the machines ourselves using atoms with Bohr orbits. And here is a trap for single ions, single atoms, that you can trap in between these electrodes. And you can have maybe a few hundreds of these. And then you have your 100-bit computer. And then we do calculations of these atoms. And this is another experiment with neutral atoms. And every green dot is actually an experimental picture. This is also an experimental picture of real single atoms trapped in space. And you can see from the lower right corner here that this is actually an experimental group in Paris, because they just couldn't resist making a little Eiffel Tower out of the atoms. But when you do computing with them, you put them boringly on a square, of course. But they can do everything, these guys. Another thing is electronics. So actually, if you take a normal electronic component and you cool them down so they're superconducting, and you cool them very well down, control them very well, remove all impurities, then you can actually also have quantum currents running in these devices. So here's just the first IBM 5-bit chip, and this is how it's all mounted inside a fridge. This is the fridge is open, then they close it, and then everything is kept very close to absolute zero. And these are the big industrial attempts by IBM and Google and also across the world actually to build these machines. So there's quite a number of companies building quantum computers. And now it looks complicated, but of course they make it more and more fancy. So these are actually the chips in which there can be 50s or 100s or even several hundred of these little bits sitting in a beautiful centimeter large chip. So of course that's all very nice. How far have we come? Well, it started looking like experiments, and now it looks like chips. This is an atomic chip where the ions are floating, the atoms are floating over the chip surface. And you can actually buy these machines, or you can access them via the internet, via Amazon, and then you can do your own calculations with these machines. Are they good? No, they're really bad. They're really bad. But of course, they do progress all the time. So the last fantastic result came from Google just before Christmas. They had made a new chip called the Willow chip. This has 121 qubits. That's the good news. The bad news, every 100 operations, there's an error on every bit, okay? So it means it's extremely forgetful. If you do just one clock cycle, just one calculation, you're almost certain to have an error because you have 100 bits, and there's a 1% chance of an error. Okay. The big thing they showed was that if instead of storing 100 bits on their 100 bits, they only try to store one, but in a global way, so they keep using the other particles to correct the error. They could make the lifetime better. So now there's only an error on that single bit every 1,000 times those. Okay. So Google has demonstrated a single bit that can last for a millisecond. Okay. But before that, their single bit would only last for a tenth of that. So that's what we call progress. Okay. But of course, we want the error to not be 1 in 1,000. We want the error to be 1 in a billion because we want to do hard calculations. And that means that the number of physical bits to store a single logical bit is going to explode to millions. So the quantum computer we try to build now will probably contain billions or many hundred millions of physical bits. They should all be connected. They should do all of that. And we have already been at it for 20 years. Because we started doing this 20 years ago. So I'm not sure in my lifetime I will actually see anything useful being done with a quantum computer. Does that mean 10? Oh, that's a lot of time. Thank you very much. Then I should almost go back to Paul. I won't. I will finish, and then I will get a good question about the architecture from somebody in the audience. So the quantum computer is just fantastic, and it's progress all the time. Right? But when you hear the news, when you see the front pages, you could always just check, okay, so where are we actually now? And then, of course, they will ask people like me or some other researchers in the field, and if they ask me in Danish media, so what is the latest Google result? I will say it's fantastic, because this is a fantastic breakthrough, because before that we were even worse. Okay. But also I try to get the time with the journalists to say, so now we only need 10 billion more steps of the same magnitude, and then we might actually have the computer. And they don't, even if I tell them, they will not print it. But that's okay. It's super exciting. And for young people in the room, please come and study in this field, because it's so much fun. And so I have contributed, actually invented the way this calculation works in this particular setup. And that's the best gate that exists in the world to this day. So you can make contributions to every little way you reduce the error by a factor of 10. Wow, it's worth a lot. Every way you can make it a little bit faster. Every way you technically can build a component who has fewer errors in it. Fantastic. So that's all branches of physics and chemistry contribute here. I like to finish instead with a reflection that we often hear. So people, if I say to people in a public debate, quantum computers are far into the future, they will remind me of the classical computer. And there are many funny quotes from the 1970s, people saying we will only need one computer in Europe. And today, the computer they were talking about was less powerful than this program. And we all have several of them, right? We even carry them around, use them all the time. So it was not imagined how we would use these machines. So therefore, they think we can be equally optimistic with the quantum computer. But of course, it's physics that also says how well it can actually work. But it's still interesting. So here is the first transistor, 1947. It was the size of a fist. And today, of course, we have billions on a size of my fingernail. And what happened here? Is that something that was useful already from the very beginning? This is very, very not useful, this little device. And it took a long time before you could put many on the chip. But there was actually one application already in 1950, 1951. And I love it, and I love to talk about this. This lady is holding in her hand a device that contains only one single transistor. And it changed her life, and it changed millions of people's life to the better. Okay? Do you have any idea what the single transistor could do that was so fantastic? Yeah, that's right. But did that only change our life to the better? It's better than the radio. But it's also true the transistor is also in the radio. That's why we call it transistor radio. It's the same reason that it sits in that device. That device is a hearing aid because the transistor allows you to do electronic amplification. So you can amplify signals with a transistor. It allows the signal to go through. If there's a weak signal, the stronger signal can go through. That's amplification. And that's also the principle in the transistor radio. But here it's also what makes a hearing aid tiny. Because before that, the electronic amplification was done with radio tubes. Maybe some of you know the old radio tube radios, and there are also people, electric guitar fanatics. They will have a radio tube amplifier because of its nice properties and good sound, but they would be batteried by 6 kilograms of batteries. And the power for these was enormous. Now this thing is batteried with a battery which is inside. So suddenly, we have completely transformative change of lots of people's lives. It is my dream to actually take one of our little things in quantum and just find that kind of application. And of course, I'm not the only one. We actually already do it to a large extent. So what is one person's computer is another person's sensor. A gadget, a device, which is very sensitive to something. What makes the computer very fragile is that all the bits are very sensitive to be disturbed. But that also means that such a bit is also very sensitive to what it disturbs it. It could be a magnetic field. But that means my atom is a good sensor for magnetic fields. It could be a phone signal. Then I can sense if there's a phone signal. Maybe I could put it into a phone and have a better receiver for my phone. Or it could be many, many other things. So we are actually building now sensors where we use the fact that these circuits are very fragile and not very good for computing to instead use them to sense what kills the computer. And that could be motion sensing in navigation, better GPS system, element analysis, find out which atoms are in your surrounding in a chemistry process. Because the single atom you're looking at changes its frequencies because it interacts with the other atoms. And there are many, many very exciting protocols for that included right now. And diagnostics in medicine. We already now do experiments where people are having little gas cells with atoms in a helmet, and then you can see their brain waves. That's much more flexible and smart than the old system where it was actually half a ton of a machine and you had to put your head into the machine. Now we can monitor children when they're playing because they just have this little cap, and on that they're sitting these many sensors. We can see why they have epileptic seizures or what we're talking about. Hearts, a little gas of atoms on my chest can measure the magnetic field, which comes from the electric currents in my heart, and which can diagnose if I have issues with my heart. So we're actually working on that all over the world. It's very exciting. And I think this is maybe where some of the technologies will go first, and then in the long run, they will go back to the quantum computer. That brought me to the end. And of course, I have to, as a Dane, I have to finish with a picture of Niels Bohr. Niels Bohr said many funny things, and towards the end of his life, just a week before he died, he actually said the following about quantum mechanics. Should we one day wake up and realize it all been just a dream, we would still have learned something. Learn something about the way people think, the way reality works, the way we perceive reality is what he had. I think we can maybe say the same about quantum computers, that even if we don't manage to build them in the end, we still learned a lot of physics in our attempt to try to do that. So with this, thank you for your attention. Yes. You would like to hear the Dirac story? Thank you very much. I felt so sorry, and I even got a little sign that I had a little bit more time. So now I just go back to Dirac's, because this is a magic thing. When you do something which is using abstract mathematics, then sometimes mathematics shows you something that you have to understand afterwards, a bit like the Schrödinger equation itself. So this is Paul Dirac, and Paul Dirac was sitting in 1928, and he said, that's very good Schrödinger equation, I like it. Who doesn't like the Schrödinger equation? But the Schrödinger equation is actually coding for the classical mechanics. So it can solve the same problems as Newton's law could do, but now quantum instead. And it worked wonderfully, as we saw with hydrogen. But there's a correction to classical mechanics. The thing goes very fast. Then it's called special relativity. And then the formulas change. It's not Newton's law. So there's a formula for energy, and I guess many of you have seen Einstein's famous equation, E is equal to mc squared. So there's a relation between mass and energy, and we can actually convert mass into energy, and that's what happens in nuclear processes and in particle physics processes. Now, I will show you not that equation, but Einstein's not so famous equation, which is the same equation, but I've taken the square of the energy. So instead of saying E is equal to mc squared, it now says E squared is equal to m squared c to the fourth power. That's exactly the same as before. But if the particle is also moving, it has more energy than just mc squared. And this p is the momentum of the particle. That's equivalent to the velocity times mass in classical physics. So a moving particle in special relativity has an energy who solves this equation. And Dirac, he coded that into a wave equation. So he made the Schrödinger equation where this is the energy, rather than the formula that Schrödinger did. And he's got a lot of funny results. And I don't even have to show you Dirac's equation, because already this classical equation showed what Dirac stumbled over. If I have an expression for what is the energy squared, then of course it doesn't tell me what is the energy. I have to do a little bit of math in my head. So if the energy is 20 squared is 25, then what is the energy? So it's 5. But as you also said, there's two solutions. There's also minus 5, because minus times minus gives plus. Right? And normally we throw that solution away. I mean, if I told you that I have to build something in my house, so I need to something that has the area of 2 square meters. So how big should it be? And of course, it should be square root of 2 times square root of 2 if it's a square. That's the solution. And you wouldn't go down to the local shop and say, I like to buy something which is minus square root of 2 and minus square root of 2 on both sides. But it would also solve the math problem, but it's not the physics problem. Right? But when you do the math, also in Dirac's more abstract way, he found all these extra solutions. And he said, I better keep them. Who knows what are the right solutions? This is such a strange theory. So he kept both the positive energy solutions, the one with energy mc squared and higher, because they are the normal ones. But then, of course, the negative value minus mc squared and further down also solves that equation. That would be a disaster, because if you have an electron who is described by this Schrödinger equation, in Bohr's model, if you are in a high energy state, you can fall to the low energy state and emit light. And if there are lots of states down here, you can fall from that state into any of these states down here. And all matter would turn into light, because it will release all this energy into light. There's one solution, and in the Bohr model, the solution was there can only be one electron in each orbit. So the outer electrons cannot fall into the inner ones, because there's already an electron sitting there. So Dirac said, maybe all these states are already full of electrons. That's why I put all these little minus balls here. That's just to say that, yes, but the whole world is already full of all these electrons. So we're actually walking around in a soup of electrons who have these crazy negative energies. But for that reason, a real electron sitting up there cannot fall down there, because there's no room for it. Okay, that just sounds fun, right? But now we can do something crazy. I can come in with a lot of energy, and I can lift an electron from a low orbit to a high orbit, like we did in the Bohr atom. In this case, I can lift it from this sea of negative energy into the sea of positive energy. So now I have a hole down here and a particle up there. This guy is negatively charged. If I put a voltage, it will move because it will be pushed by the charge. Down here, well, what is really going to happen is that this is the hole, but all these electrons feel the push. So now it will be possible for this one to actually move to the right because there's room for it. Then there's room for this one to move here because there's room for it. And what you see is that all these particles can now move. But what is the net effect is that the hole is moving in the opposite direction. And it's a little bit the same, you know, if you come late for a talk like this and there's an empty space right there, and the guy is standing out here and says, could you move in? And then first you would move, and then you would move, and then you would move. Of course, it would be people moving, but in some sense, it's the empty chair who moves out. So that's how the nerdy physicist sees it. Right? I don't see the people. I just see there's an empty chair going the opposite direction. So this hole that you have created is actually like a positively charged particle who does the opposite of the electron, and together with the electron is created from pure energy, and it can always fall back down again, and then they turn back to energy again. So that's the first proposal in the physics literature of an antiparticle, the opposite of the electron, being just predicted by the theory as this kind of phenomenon, this positive hole moving the other way. And it was discovered experimentally in 1932, just 4 years later. It does exist, it's the positron. Called the positron, and it's a very useful particle, as I write here, so I just have to show it to you. because when an electron and a positron meet each other, they disappear and they become energy. And they always become energy in the form of two light quanta that go back to back away from the point where they were created. So if you eat certain radioactive material, they will emit these anti-electrons, positrons. And as soon as they meet an electron in the tissue around that point, they will send out two X-rays. So you take a patient and you put her in a scanner, and then she eats this cobalt or some other material. It's not dangerous at all, it's very low dose. But this little positron meets an electron in her brain, and then it ejects signal. And from where you see this and this photon here and here, you can go through the straight line. You know exactly where in her brain this happened. And that means you can know where in her brain was this atom actually sitting. And that means that if this is together with some nutrition, you can see where does the nutrition go in the brain, where's the activity in the brain, and we have diagnosed where different cognitive processes are actually located in the brain with millimeter precision using this. Typically, it's also used for, of course, diagnostics. If you have an accident, you want to see if there's a brain damage, and then you can make this kind of scanning to see if the brain activities are normal in that person's brain. So it's a wonderful story. Again, this is a 20th century quantum applications, but actually coming out of this sorting equation, right, as a free bonus. Amazing. Thank you for asking the question. Thank you for accepting my urge to ask that question.
Yeah, any more questions, especially from the back? We'll start from the back. Yes, please.
We like the questions from the back to exercise the people with the microphones.
You know, there are logic gates for classical computers.
Yes.
So how does logic work in quantum computers?
Wonderful question. When we built the quantum computer, we are extremely inspired by the logical gates in quantum classical computers. In some sense, it sounds as we should mostly just do the initial state, being 0 and 1, but then after that we do all the same as the classical computer does. So in a classical computer, if you have a bit, you can choose to do nothing, or you can choose to flip it. That's essentially what you can do to a bit. And that operation, not as we call it, is also a quantum operation. But when I do it on a quantum bit who is both 0 and 1, then it becomes both 1 and 0, because the 0 part becomes a 1 and the 1 becomes a 0. But the gate is actually the same. Then there's a little thing, I'll just say that too. But of course, in classical logic, there's something called the exclusive OR, which is an operation who checks, are they the same, and is one of them one? And that kind of question we also ask to the quantum computer. We call it controlled not, because it does the same. If 1 is 0, keep the other one. If it is 1, flip the other one. And that outcome is actually the exclusive OR on those two particles. So we are extremely inspired. Now, a difference. In quantum physics, the time evolution is reversible. You can solve the Schrödinger equation backwards. So you can always go back, see where you came from. Also in classical mechanics, if I have a stone who hit the ground, I can also calculate where it was, at which height earlier on. And that's not true for classical logic, unless you choose a version that's called reversible logic. So in classical computers, you just delete data. You can also copy data. You can do many things to data which is not according to quantum laws. So our gates are all reversible because we actually keep everything. If I have 2 bits coming in, your and or is only giving 1 bit out. But I always keep 2 bits out. Maybe one is the and answer, and the other one is just enough that I can go back again. But that's a small technicality. So we do get a lot of inspiration. We think about complexity the same way as in classical computing, but we just add this feature of superposition.
Evening, Professor. Thanks for the talk. Can you deliberate on how gravitational lensing is related to quantum phenomena?
Yes. So the gravitational lensing is not. It's not important that it's a gravitational lens. I could actually also have 2 good colleagues with bicycles who were riding with their bicycles with some quantum particles that they give to me who have a common origin. And then I could measure on these particles. The thing that the gravitational lensing does is that it gives us 2 spots in the sky who came from the same source. We also have, so you know, that's a fantastic thing where you can have an image where it's the same source, so you can measure those clicks coming from 2 different directions and knowing that it's actually the same collection of atoms who emitted that light. I will admit that we do another experiment on this in astronomy, which is harder to see connected to Einstein paradox, and that is if I'm looking at the light from a single atom, I can see a click in my detector. the atom has gone to the inner orbit in the Bohr picture, I cannot see another click immediately afterwards because the atom has to be excited again. And that gives a statistical correlation in the noise in such a detector. And we also see that in astronomy. And the only real explanation for why the source can be quiet after a click is because it was a click who made it quiet in the next interval. I mean, this statistical correlation cannot be mimicked by classical noise sources, but only by quantum noise sources. So you can say we validate this measurement back action effect, this effect that when I measure something, it changes the state somewhere else in the system. But of course, it's technical, and the proof that it cannot be explained classically is much harder. But as a narrative, there are many of these astronomical phenomena that have a very good and simple quantum explanation, but it also involves how the measurement actually makes a particle far away change its state. It even changes its state in the past, because the light photon I see has been traveling for maybe a billion years. And when I do the click, I say, oh gosh, that was amazing, I actually changed the past. But I also sometimes, when my daughters were sick, I would call my brother-in-law and say, could you or your wife come and look after them for a few hours? And then one of them would leave. I wouldn't know who left. But as soon as I opened the door, when the doorbell rang, I would see who left half an hour ago. Because that's the person who was here now. So everything you see now also tells you about the past, right? That it's archaeologists, I mean, they also learn about the past. So if quantum states are states of knowledge, there's actually no conflict in changing my knowledge about the past. That's because I learned something now about what happened in the past. What makes quantum crazy is that, in fact, it would not have happened in the past if I had not learned it now. Because that event I'm talking about is not a real event in the microscopic world. It's again my knowledge about the next measurement I could do on the system. So yeah, fantastic. Attack me afterwards. We can discuss it further.
Thank you for the talk. So I basically have two questions.
Yeah.
The first one is regarding the theory of quantum gravity.
Yes.
And how is it different from our current understanding of curvature of space-time, that is gravity? And the second question is regarding the property of charge.
Yes.
So where do electrons get their charge from? Like
Yes.
we have Higgs bosons to account for mass. So what is the counterpart of charge for that?
Yes, so of course I'm not going to give very long answers from two reasons. One is I don't know very good well the answers, and two, even if I knew it would not be the good form. But the first thing with gravity is, I mean, it's very exciting. Gravity is a complicated thing because gravity is the forces between things that have mass. But in fact, in Einstein's gravity, it deforms space. And when space is deformed, of course, it also deforms the effective interactions between the matter. So the whole space, it's kind of non-linearly coupled. The mass distributions live in that space, which they are creating themselves because it has this curvature. So that makes that theory different from other physical theories. Electromagnetism, we have also forces, but they don't change the space. So we have fields, but that field is living on the original space. So that makes it hard in one way. It's not true that one cannot quantize gravity. Feynman quantized gravity, but away from black holes and away from the big universe. So I can quantize gravity in this room. So quantum gravity can be quantized at that lower scale, but I cannot go into the whole universe where these curvature effects get important. And that is a big missing point. So I completely agree with that. And I mean, there are different funny things. Penrose had ideas about gravity being itself a quantum effect coming because of, and maybe even that gravity could explain what happens in measurements. Why do things actually collapse? Maybe it could be this coupling to gravity, but that's very unclear. But technically, gravity is very hard because of this thing, and people have tried, and they have only been able to locally make a theory that quantizes gravity. The electric forces, it's different. We can quantize completely the electric field, magnetic field, the particle motion, and that's a model that works. So it's very much technical. The other question about why is charge quantized? It's not a completely and full argument, but there have been different thought experiments to show that charge has to be quantized. For example, if you're moving around a charged particle or a wire or things like that, then if you want the wave function, the state, to be insensitive, if you complete a complete turn, it should be the same state again. And some of these equivalences actually don't force charge to be quantized, but you can have some kind of consistency that likes quantized charges. It's still a bit of a mystery, right? The standard model says that the quarks have charges of 1/3 and 2/3, and they can, three of them always add up to something which is an integer. So that's the charge of the proton and the neutron. some quarks and their anti-quark, they can give you charges also, which could be 0 or 1. And so it works, but I mean, why it is fundamentally like that? There are new modern theories in conformal field theory where actually I had a student who is much smarter than me, and she's now working on this very theoretical stuff. And she made what we call a lattice model. So she put space into little grid points, and then she calculated on that grid, and then she found that there were some topological structures, and they came out with a charge which was like 1/3. And in real solids, in superconductivity phenomena, there's something called Laughlin state, which are also quantized in these rational charge numbers. So one thing is we can measure the equal charges, but we can actually, in a system composed only of electrons who have charge 1, we can see effective charge 1/3 and 2/3 appear in structures, right? Also other fractions. So there is something beautiful, and maybe it's, we are natural scientists, so we don't know if it's the truth we're looking at. We look at the description who describes what we see now, and that's probably also true with this integer charge. Tomorrow or 100 years from now, they find a 1.1 charge, and then bang, everything is open again. But so far, we have a beautiful theory that captures all this charge phenomenon. And then you have to ask a particle physicist how much they believe in it and how robust it is to attacks.
Sir, my question is regarding multiple qubits. How should we perceive when they are entangled?
Yes, that's a wonderful question. And in fact, so maybe I could just jump to an example of those qubits, because I showed you this implementations of. So of course, this is just a drawing by me. But if you want to do computations where they become entangled, as we call it, then you have to have an interaction between them. And that's the same thing in the transistor, that there's actually physical forces that makes two wires produce a result. So I show you here the 7 qubits in Ike's beautiful experiments. These yellow ones, these are the fluor atoms in that molecule. And the little arrow is because fluor atoms have a spin 1/2 property. It means they're little magnets. And the little magnet can point up or down. So he puts a strong magnetic field and they can point up and down. They have different energy when they are up and down because they are against or in the same direction as the magnetic field. And if you come with a frequency which is equal to that energy, again this Bohr frequency condition, you can flip the spin. That's what they do in hospitals. So when they do scanning of me in a hospital, I had a broken disc some years ago, then they're actually flipping the spins in my back, the protons in the water molecules in my back. And then they can see where the protons are sitting because they absorb that signal. So that is the way we can rotate 1 bit. And I can rotate it from 0 to 1, but if I do only half the time, it makes it into 0 and 1 at the same time. Very nice. Now this guy is sitting just underneath that one. And maybe you can even feel it in your hands. If I give you 2 magnets, they are attracting each other if they are like this. But if you put them North Pole against North Pole, they are repelling each other. So there's a difference between the energy of that one depending on the orientation of this one down here. So all by itself, if I shine light on that one, who will flip it? It will only work if this one points up and not work if it points down, because the radiation doesn't fit. So that's the trick these guys used. I mean, find a way to make what you do to one particle depend on the state of the other particle and make it work even if the other particle is both up and down. Because if the story is this is up and this is up, I flip it down and this is still up. And this one is 0, I keep it. What if it is both 1 and 0? Then I both flip and not flip. And then they become literally entangled. Then we get the state where they are both pointing up or they are both pointing down. And that's what we call an entangled state. So it's, of course, it's technical and it's different in the other proposals I showed. Yes, so it's the same story. Okay, lovely. I apologize that I'm misusing this question to talk about something I really love myself, because not so much in this proposal, but in the atomic proposals that I've been working on myself, both the trapped ions and the trapped neutral atoms, you can actually shine light on one of these ions. It gives a little push to them and it starts moving. All the other ions feel that motion. So in fact, they will all drift from side to side. And therefore, when I shine light on any 2 of these or on all of them at the same time, I actually correlate them into an entangled state. So we proposed, and that's already year 2000, shine 2 colors of light on all these particles, and they will all become entangled. And that works. So it's about using forces that exist mutually between all the particles, such that when you drive one, everybody feels it. And we can do the same with the atoms. when I talk to computer scientists about it, we had a good question about analogy to classical computing. They're not excited. I mean, I went to them and said, look, I can do 10 parallel gate operations at the same time. And then the guy, he said, can you do an exponentially large number at the same time? Because factor 10 faster is good if you're a physicist, but computer scientists don't care. They want a scaling with the problem to be, is it n squared or n? I mean, is it getting quadratically harder to solve the problem when it's getting bigger? If I give them a factor 10 or something, that's something they don't even care about. It has nothing to do with the complexity class, this kind of factor in front. But for me, this kind of multi-qubit gates are very important. I save so much effort. And just coming back to the question from the back, if I want to do some of these complicated full algorithms, they are often written out in terms of super many 1 and 2 bit gates. That's how your computer works. And finding the most effective way to solve a real problem in terms of 1 and 2 bit gates is a very hard problem, where having direct access to do many at the same time, something I like. But we could also just sequentially. I mean, I could have taken this one, flip this one conditionally, then you could flip this one condition on that one, this one condition on that one, this one condition on this one, then they would actually all become entangled. And they would either all be flipped or all be not flipped. And so you can do it in many ways.
So I actually have two questions.
Yes.
One is on the mathematical side of it,
Yes.
where you said we can use the wave function to find the probability of a particle being at point X. Why are you taking an absolute of it and then again taking a square of it? And my second question is, I've heard that the chip of the quantum computer is actually really small, and it's the cooling mechanism of it that's so huge. So will it ever become small? Is there a way to make it smaller?
Thank you. These are two fantastic questions. Since I'm just here on this slide, I will go first to the size question, which is a really good question. All these computers have a fairly big footprint. I mean, in the lab, they actually take up a little too much space because classical data are very easy to protect. And therefore, we can also put the data close. But these bits will disturb each other because I have to do something on one bit, and the next bit is sitting just next to it. So if I shine light on one, maybe some of that light will hit the other one. And the same with the superconducting qubit. So far, the quantum computer chips are too big. And Google makes this fantastic chip. It's this big, and it has 100 bits on it. And I mean, in your pocket, you may have a phone which is so small, and it has 1 billion. So we are still not very good at making them small. And this problem will stay with us, but with good material science, we can make them smaller. So it's going the right way. And you're also right, they have to be cooled. So this is the big fridge where they have to go very cold. And you're absolutely right that it's going to be very difficult. These fridges are now so big. The physical experiment is so big. So how will we get 1 billion particles in this area? We have to scale to something bigger, but we cannot build the fridge that big. Maybe we have to build many fridges and couple them with cables, and then we can have a computer distributed like that. And engineers are working on the question you asked. Very good question. The math question, that's a wonderful question. There is a term that I did not explain to you in the Schrödinger equation. It's just one little letter here. This little letter I, sitting here in front. That's a crazy number. It's the square root of -1. So which number multiplied by itself gives a negative number? That's something I did not learn in school, but only in university. So the wave function is not like the water wave, something that has a height everywhere. It actually has a value which is not even a number that makes sense to us, because it can be this kind of negative number. But if I take the absolute square, it's called, then it becomes a positive number. And I don't like negative probabilities. Of course, that's not a good argument why it's the right theory. But it is only the absolute value squared of that number who becomes the probability. Why does it then have to have this complicated complex form? That's because sometimes the wave comes from different sides and you have to sum them before you square. And you know, if you take two numbers and you add them together and you square, that's not the same as first taking positive numbers and then adding. If I come with 1 squared, it gives 2. But if I come with 1 and -1, then it gives 0. So this interference, dark and bright stripes, is because of this interference. And this little I is what controls where these stripes they are. So it's of course mathematics, right? And it's a funny discovery. Engineers have been using eyes also in electro circuit analysis before, just as a nice way to visualize the numbers. But they will also always take a real number, as we call it, a component out of it. Wonderful question. Please write back to me when you have solved some of these problems. I'd like to see the answers.
So I'm sure a lot of you have different questions. We have a lot of questions online. We'll take them and then come back to the offline questions. So Hemant is asking, how exactly does the quantum computing algorithm interfere with the results?
Sorry, how much?
How exactly does the quantum computing algorithm interfere with the results?
Quantum computing and
Algorithm.
Yes. So it's actually a very good question. The algorithm is the one who says what should we do in every little step of our calculation, right? So if you want to calculate something, maybe you write a code, and the code says now you have to sum that number and that number. Now you have to multiply this with that, and you have to add everything. So there are steps who finally lead to the result. And that is the Shaw and the Grow algorithm. They are the steps we have to do to all these bit values, such that we are going from posing the problem to actually finding the answer to the problem. And how do we do it in a quantum computer? Well, the steps are what we literally have to physically do at each step. And we do it classically. I'm a guy in the lab, and I know if I have to flip a bit, I have to apply maybe a pulse of light who has just the energy to flip that thing. If I have to flip it only half, then I take the pulse for half the duration. So all these gates, as we talked about before, they are applied by me. And then I just do the sequence operations that make the algorithm. And then, of course, you say you are finished with your quantum computation when you have done all the steps. And then you have to read out what was the answer. So there's a steep interplay, and the researchers in this field are composed of the experts in making the algorithms, and then, of course, the more hardcore experimentalists who find the physical component who can do it. But maybe one aspect of the question could be that is it particular quantum what you have to do? I mean, there's a quantum thing inside the fridge, right? But me outside the fridge, I'm not a quantum person. I use classical instructions to what I should do. But I just know that when I turn on classically this laser and turn it off again, then the atom has done something quantum because it received that light. So that's maybe the game between the algorithm and the quantum lesson.
Right. On that note, Dharmendra is asking what computer algebra and computer language will be required or is required for quantum computers?
Super good question. The field is now so advanced, so people have already started writing compilers. So you can actually go on the internet. The best source for a long time was IBM. So they have a thing called IBM Q or IBM Quantum. And they made a toolbox called Qiskit. And there you can see the algorithms, the same way as classical algorithms are sometimes shown as a diagram where all the gates are shown one after the other. And you can actually go and build it yourself. And then you can both simulate on a classical machine what it does, solve the Schrödinger equation, but you can actually also run it on IBM's physical computers. And so that's already a kind of language. And now they have actually turned it into, you can instead of sit and putting it with a box and little boxes as a diagram, you can write it yourself in Python. So there's a programming language called Python, and Python now comes, you just have to define the quantum bit rotation as an operation in Python. Mathematically, it's represented by matrices and linear algebra, because the solution of a Schrödinger equation can be described by a vector who's undergoing these transformations. This is a mathematical technical thing, but the mathematical language of the Schrödinger equation can be coded, and the same operations can also be coded. Python is not the only one. Now there's tons of them out where there's a thing called Kibo, which is maintained also from Singapore and other places. Most of the manufacturers of these machines have made their own library, published it, made it publicly available. In China, they have a project called Quafu, superconducting quantum computer. If you go on their webpage, it's also a Python programming language. But in fact, C++, Julia, I would say almost any modern high-level language has also its quantum compiler. And you can define, of course, your own structure. So when I invented my own gate, it's actually, that's a command. There's a command in the Python book. I didn't code it myself, but somebody found it useful, and there was a kind that they put my name on it. So I'm a command in the Python. I don't know if that's good or bad.
So Rajesh is asking, currently, is there any sensor based on quantum mechanics applications?
Yes, so that's also a good question, because in some sense, many of our high technology sensors work because there are quantum systems involved. We do use atoms to sense things. It's first quantum revolution. It's not the mysteries, it's just the fact that atoms like certain frequencies, therefore they are good at that kind of stuff. The next level where we use entanglement, where we use quantum information-inspired ideas, we can demonstrate and publish articles, a lot of them, But it's always a question, could you have obtained the same precision just having a better system and operated classically? And it's almost always the case that you do better by just having more atoms and doing classical. The states are more robust, it's a more robust technology. But there's one experiment in the world now which is completely relying on quantum light, and that's LIGO. There's an apparatus who measures gravitational waves. So when a billion years ago, two black holes collided, it was such a violent thing, they curved space, wrapped space in such a crazy way that it led to a wave that propagated all the way through space. And every month we see a few of these events making mirrors shake. Okay, the mirrors are 4 kilometers apart, they weigh 40 kilograms, they shake by 10 to minus 21 meters. They shake by a millionth of the size of a proton, okay, the size of an atomic nucleus, but they can measure it. And when they got to this quantum light for measuring it, they actually increased the sensitivity by a factor of 10. And it means that now they will see 10 times as many events, and they will therefore start doing not only say hooray and drink champagne every time they see an event, now they're actually going to do statistics and do science. So LIGO has gone from being a fundamental thing to prove the existence of gravitational waves to become a new observatory looking into space. And that could not have been done without the quantum light. So that, I think, is a cornerstone example. But we will probably see more and more local testing. I can have a single atomic defect in a little solid and can measure within few nanometers what are the other atoms sitting there. Can you imagine a use for that? Well, at some point, maybe you can. I mean, maybe you want to make very pure material, and then this could be the little probe testing if it is pure enough already. Certainly for basic science, we already use a lot of quantum sensing right there.
Evening, Professor. I just had a question about the interpretation of quantum mechanics.
Yes.
So the Copenhagen interpretation, it tells you how to calculate what happens, but it doesn't tell you how anything happens, right?
Nope.
The underlying thing.
Nope.
Yeah. I mean, Bohr was just fine with it, but Einstein was troubled with the fact.
Yes.
But there was another interpretation, right? The Broglie-Bohm interpretation, the pilot wave theory. So why is that not widely accepted? It gives you what happens, right? Like particle interacting with.
So I love the de Broglie-Bohm theory. So de Broglie, who was the guy with the waves I mentioned before, he came up with a beautiful idea, which literally, not literally, but which we can translate to say, it's a little bit like when I flew in with an aeroplane actually at 5 this morning. and you are in a plane, but the pilot is not only touching the environment with the plane to see if it's safe, he uses a radar wave. So you're having a radar wave who is informing you where is it safe to fly. And in some, de Broglie's proposal was that maybe there was a real particle moving around, but it was guided by a radar wave. And that wave is called sometimes the de Broglie wave or the pilot wave theory, because it's the pilot using it on a ship or a plane. And so the Schrödinger wave function is actually that pilot wave who affects which motion you choose to make, the way that ships and planes do it. And that's beautiful. And it's wonderful theory. And I mean, it doesn't give anything new, because the pilot's trajectories here, the orbit, will just follow exactly the same law as the Bohr rule. And if you don't know where they started, then they will also form the same probabilities and the same possibilities as the quantum mechanics. So that's why some people don't like it. I like it. I think it's great, because it finally gives us actually an intuitive picture of something. But don't be too excited about it, because it's also a wild one. Because then those two particles have real positions which are also being correlated. And when I measure something on that one, that changes the big wave function. And that change in the big wave function means that this guy now feels a new pilot wave. So effects can instantaneously transmit through space in a way that has to be interpreted as being real now, because this orbit, so you have two pilots flying, but it's not a radio signal. The guy says, I warn you, there's bad weather ahead of you. It's instantaneous. When he sees it, the other guy also sees it. So that's what makes it mysterious. And so together with pilot wave theory, de Broglie and Bohm in particular, later times, made a whole world view, something they call the implicate order, which is a kind of ordering of correlations in nature, which for some is not so advertised. So I mean, that's reaction against the Bohr. I think it's pretty fantastic. Another interpretation I just want to tell you is the people who believe that the wave function is real. They believe that nothing random ever happens, because everything that's possible all happens. Okay? But it happens because in the way that we can understand if we are quantum ourselves. Because if I have a particle who can be in 4 different positions, instead of thinking that what happens is that it is only one answer coming out, it is in the left point because I see it in the left point. But at the same time, the quantum state of the particle and me has the particle here and me thinking it was there, because I'm also a quantum particle. So I become part of the Schrödinger equation. And now all these phenomena are never random, but they just become quantum states of me. And the fun thing is, of course, I see where it is, I tell you. So now you all heard me saying it was to the left, but you also, sitting in the same room, you all heard me saying it was to the right. That kind of craziness was originally discarded. We would have seen that because it gives conflict. There's not one single conflict. There's never disagreement in the room. We all completely agree on what we're talking about, left, and we all agree on right. But there's no situation where you think left and you think right. Right. So the world where we think things collapses will look the same as such a world. But in that world, there's no randomness. In that world, there's a deterministic law that just says everything goes forward. So that is probably among the philosophers of quantum physics, the one who is favored. I like that even less than the Bohr. I mean, that's personal. I have different religious views, political views than other people. Doesn't mean I'm right. Just means that there are things that triggers my imagination better than other pictures. So I mean, I think it's a richness of quantum physics that there are different interpretations. It's a richness because one community can get ideas the other community cannot get. And I would actually say that quantum computing as an idea is due to this many universe interpretation. To very literally think that you have different possibilities at the same time. That's a language Bohr would not allow me to use if he was still alive, but it's very constructive in your mind because it's parallel computing, because we do everything at the same time. So I think that we owe a lot to the different interpretations. And I encourage all students, I encourage myself to never, I don't discard any interpretation of quantum mechanics. I don't talk bad about any interpretation of quantum mechanics. I don't look for the weaknesses in the arguments. I look for the strength in the arguments of any interpretation because they are source of inspiration.
Okay. Okay, any one last question from there? Yeah.
Just wait for the microphone, yes. Also for the audience on Zoom.
Thank you. So, pardon me for the out of my question. Basically, I don't know. So you said about the quantum physics mechanics, which actually is not like the conversation which is happening with Einstein, right? So he was telling the wavelength was not it cannot explain the system that we are working on, right? So basically black holes, which actually where the uncertainty and the randomness of so complicates. So do you think like quantum mechanics could be the like anything can be understood? What about in the black holes?
So I mean, the problem is to make this big quantum theory, to make the full Schrödinger equation for a black hole. Of course, there's other aspects of black holes that we really do like to understand. So we do like to understand what is it that happens when thing falls into a black hole. And for that, I don't need to know how it looks all the way around the black hole. I just want to know what is happening through this surface. And there's a paradox with black holes because there's information going lost. And how can that actually happen? Because everything is physical law, so everything should be a principle conserving information. And the black hole doesn't remember the books that you throw into it. It remembers how heavy it is and how fast it rotates. But Shakespeare's collected works are sort of lost in the black hole. No resolution to that paradox comes from quantum physics. And it comes from quantum physics because black holes, at the interface where you fall into the black hole, there's actually radiation coming the other way. And if you make models, just local models, they can be made for what is happening at that interface, then you can actually see that that information is in principle retrievable in what goes the other way. So you know, that is one place where quantum locally can explain a property of black hole, which is very important and hard to understand. And then, of course, there's this bigger problem. Do we have the grand unified theory of gravity and quantum? And to that, the answer is no. We do have the grand unified theories of all other forces, nuclear forces, all of that works, but gravity has not been put there yet. And it's disappointing because we do have the classic theory for gravity. I mean, the Einstein general relativity. So, but it's a technical thing more than maybe maybe there's no physics we cannot do. because we can always view at it as a local problem.
Thank you, sir.
Before, I'd like to make a comment. Yeah, Klaus mentioned that helium was discovered because of its spectrum in the sun. I just wanted to add that the observatory that did the observations is about 100 miles from here.
Beautiful.
In
Yes.
Guntur. It's a place called Guntur in the next state.
Yes.
And there was a solar observatory in the last century, and they noticed the spectrum there.
Right. Thank you very much.
Yeah. And the second comment is that he mentioned earlier that his youngest participant in his talks in Denmark was about 10 years old. I think we've beaten his record if you look around.
Yes, no, it's wonderful to see. I mean, yeah. I did give a talk once where there was a 10-year-old girl and a 91-year-old woman. They had both read my book, and they had both notes written all over with questions. So their arms were like that all the time. And the rest of the people in the room were not so happy because they felt that they were not prepared for that at all. It was just a wonderful experience also.
Yeah, and finally, I'd like to thank Klaus for this wonderful talk. And as a memento of this occasion, we'd like to present him with a billion atoms because he's so fond of atoms.
That's fantastic. Thank you very much. Thank you very much. And thank you for all the wonderful questions. I mean, it's a great experience to give a talk and to hear what kind of questions are coming up. And these were all very, very good questions.
Thanks for coming.